In this lecture, let's investigate some of the basic features of gravity in the weak field limit. So to do that, we must expand the metric field into or around the Minkowski background. So that would be this thing, that g mu nu is equal to Minkowski metric plus some perturbation to the metric, where this h mu nu is the perturbation and kappa is what we have been using so far, that kappa square is 32 pi g. So with the help of this metric, if I put this in the Riemann tensor, I can get, or I can derive my Ricci tensor R mu nu, and I can also, from that R mu nu, I can derive the Ricci scalar, which is R, the scalar curvature. So it turns out that if I just put this metric in the Riemann tensor that we derived in the last lecture, if I put this g mu nu in that and I derive the Ricci tensor, it turns out, or it comes out to be kappa over 2 partial mu partial lambda h lambda nu plus partial nu partial lambda h lambda nu minus partial mu partial nu h lambda lambda, which is the trace of the field h, minus the D'Lambertian operator, this is that's this box operator, on h mu nu. And we have, of course, we have a higher order terms, or the up to h squared, right, second order terms. Right, so now if I just do this thing, if I do g mu nu on r mu nu, it will give me r, the Ricci scalar, or the scalar curvature, and it turns out that this thing is kappa partial mu partial lambda h mu lambda minus the D'Lambertian operator on this h lambda lambda. And of course we have this higher order, or up to h square order terms. Right, so when we have these things, right, when we have r mu nu and r, we can write down the Einstein's field equations, right, and they are, from these equations you can write down r mu nu minus 1 by 2 r, in fact there would be an eta mu nu over here this time, and this is equal to, or equivalent to, kappa over 2. Now there is an operator now, and I'll define this operator in a bit, but it is O mu nu alpha beta on H alpha beta, and then this thing is equal to kappa squared over 4 t mu nu, where again this t mu nu is just your energy momentum tensor. So at this point it is also fitting to introduce an identity tensor, and let me write it down, identity tensor, which is I mu nu alpha beta is equal to 1 by 2 times eta mu alpha eta nu beta minus, no, in fact there's a plus sign over here, and eta mu beta eta nu alpha, right? And you'll see why this is useful in a bit. So with the help of this, now I can write down an equation for the Green's function of Einstein's field equations, right? And that is that I have this operator O alpha beta mu nu. In fact, you'll write it down as O alpha beta mu nu, and on G alpha beta gamma delta x minus y is equal to 1 by 2 I mu nu gamma delta, and you'll have your delta function in 4D, so 4 of x minus y. So this comes from your the method is the same that you adopt in your course on quantum field theory, right? And now let me define this operator O alpha beta mu nu as okay, let me write this down. So you have delta alpha mu delta nu beta, which is symmetric in mu and nu, minus eta mu nu eta alpha beta, and then you have your D'Alembert operator. And in a bit in this video I'll also write down this D'Alembert operator, as we'll see that we'll have to use gauge transformations, and we'll have to pick a gauge, and so we'll define this D'Alembert in that particular gauge. So you can your definition of the D'Alembert operator depends on the choice of gauge. That's what I'm trying to say. So, well, anyways, you will have this thing minus 2 delta again mu delta nu, which is symmetric in mu and nu, and it's also symmetric in alpha and beta, plus eta alpha beta partial, I'm just trying to save up some space now, but let's see, partial mu partial nu plus eta mu nu partial alpha partial beta. So that's how your operator is defined, this operator O alpha beta mu nu. And now from our study on the gauge field theories, we know that this operator, this one, it cannot be inverted, right? You'll have to add a gauge fixing term. You'll have to add a gauge fixing term to your equation, right? And then only you can invert this operator O alpha beta mu nu. And we have to find this inversion of this operator, because at one point we'll want to derive the Feynman rules for gravity, right? And we'll do that hopefully in the next lecture. We'll be deriving Feynman rules for gravity, right? So yes, now because of this thing that we need to add a gauge fixing term, we'll go and focus on the gauge transformations for some time, right? So let's start by considering an infinitesimal transformation of the coordinates, which is x prime mu is equal to x mu plus kappa and some xi mu of x. Now in this case, the transformed metric h prime mu nu, in fact, let's write this mu nu over here, and this thing will become h mu nu minus partial mu xi xi nu minus partial nu xi mu, right? And if you have any idea of gravitational waves, or if you have studied gravitational waves somewhat, you will be familiar with this expression, right? Now, before I go any further, let's pick a gauge. So we'll pick a gauge now, and the gauge that I'm going to pick, or in fact a particular suitable choice for the gauge, is a gauge that is called the Donder's gauge. And you can also refer to it as harmonic gauge, by the way, harmonic gauge. So they are the same thing. And it is defined by a relation that is partial mu on h mu nu minus 1 by 2 partial nu h lambda lambda vanishes, right? So it's defined by this relation. And in order for us to arrive at this gauge, we'll have to pick this xi as xi mu is equal to the Lambertian operator on xi mu, right? And this thing is just by using the definition of the Lambertian operator, it's just minus partial mu h mu nu minus 1 by 2 partial nu h lambda lambda, right? Now at this point I'm going to introduce a new field, and I'm going to call it h bar mu nu, and I'm going to set it equal to h mu nu minus 1 by 2 eta mu nu and the trace of the field h, which is h lambda lambda. Now I can do this, it's absolutely valid, right? And the reason for that is because h mu nu, the field h mu nu has a vanishing trace, right? So taking the trace of this field h, we'll see that it turns out to be 0, right? And because of that, I can completely write down this new h mu nu bar. So using this new field now, if I use this new field and put it in the Einstein's field equation, which is this one, I can write or rewrite my Einstein's field equation as Lambertian acting on h bar mu nu, which is equal to minus kappa over 2 t mu nu, right? And now this is the new or different form of the Einstein's field equation. And if you recall, if I go here, I wrote the Green's function for the Einstein's field equation over here, which is this equation, right? And I can simplify this equation with the help of this new field now, and that equation now becomes I, which is the identity tensor mu nu alpha beta minus 1 by 2 eta mu nu eta alpha beta acting on this D'Lambertian g alpha beta gamma delta, where this g is the Green's function, is equal to I mu nu gamma delta, right? And now with all of these equations in our head, I can extract the Green's function of the field h mu nu. And so upon using an ansatz, that is this g alpha beta gamma delta being equal to a, where a is just some constant, right? A times I alpha beta gamma delta plus b eta alpha beta eta gamma delta, and b is also a constant. Using this ansatz in this equation, what I find is that my a turns out to be positive 1 and b turns out to be negative 1 by 2. And hence the Green's function in the position representation, So let me write that down. Green's function in position representation then becomes or takes the form of g mu nu alpha beta is equal to 1 over 2 the Lambertian times eta mu alpha eta nu beta plus eta mu beta eta nu alpha minus eta uh, mu nu and eta alpha beta, all multiplied with this Dirac delta function, delta 4x minus y. And if I use the expression for this delta function and this D'Lambertian, I can write down this Green's function g mu nu alpha beta as in a more familiar form as minus 1 by 2 eta mu alpha eta nu beta plus eta mu beta eta nu alpha minus eta mu nu eta alpha beta times the integral over what? Integral over the momentum, right? So d4k, where this k is not kappa, it's k, which is a variable for momentum. So integral over all momentum over 2 pi raised to power 4 exponential iota times k times x minus y over k squared. So you must be again familiar with this equation. Well, it's a different equation, but the form is the same. If you're familiar with Green's functions, and of course, if you're familiar with your course on quantum field theory. Now, this Green's function, this g mu nu alpha beta, should be evaluated assuming some initial conditions, of course, and these are to be encoded by the choice of contour in the complex plane, right? And so, well, you can also define another function, by the way, and it's known as the retarded Green's function, which is g mu nu alpha beta x minus y, and this vanishes if x0 is less than y0, right? And choosing after choosing a contour in the complex plane, I can write down this function g retarded Green's function mu nu alpha beta of x, of course, is equal to 1 by 2 eta mu alpha eta nu beta, this is nu, just okay, plus eta mu beta eta nu alpha minus eta mu nu eta alpha beta times 1 over 4 pi r delta the absolute value of vector x minus x naught. Right, so that's your retarded Green's function. Now let's look at something interesting, and it's actually pretty interesting. And we'll start by noting the fact that you can write down your Einstein's field equation in a form that is this. So let me write it down. The Lambertian acting on h mu nu is equal to minus kappa over 2 t mu nu minus 1 by 2 eta mu nu times the trace of your t mu nu, which is t lambda lambda. Right. So now if I have a point source, right, for which I have the zero zero component of the energy momentum tensor as the as some constant, or let's call it mass, times the Dirac function in 3 dimensions of x, and the ij components of this energy momentum tensor are 0. So with that, I have T mu nu is equal to, or let me write down this part, right? Let me write down what this part would be. So T mu nu minus 1 by 2 eta mu nu T lambda lambda is equal to 1 by 2. Now you have the zeros as this, so you'll have m delta 3 of x, and we multiply it with, because of this this trace thing, we'll multiply it with the diagonal matrix whose entries are 1 1 1 1. Perfect. Now, if I use an ansatz, which is that the kappa times h mu nu is equal to 2 times phi g times diagonal matrix whose diagonal elements are 1 1 1, right, where this phi g is actually the gravitational potential, right? And I'll show you what I'm talking about, right? So if I use this ansatz in this above expression, this one, what I get is I'll get a solution for phi g, which turns out to be minus kappa squared times m over 32 pi, right, times 1 over r. Now what is kappa squared? We know it is 32 pi g, and we have m divided by, we have 32 pi g, we have 32 pi, and we have this r. So this r comes over here. 32 pi gets cancelled, and what you're left with is minus g m over r, which is equal to phi g. Now what is that? That is the Newton's potential, or you might also call it your Newton's law, right? And so we have recovered Newton's equations from our procedure. So that's pretty interesting, right? Now I'm going to also show you something else, which in fact I even promised you in the beginning, and that was that I'm going to show you how I can arrive at the Schrödinger's equation using everything that we have done so far, right? So we'll start with what is known as the Klein-Gordon's equation, which we know very well is this Lambertian plus m squared on phi is equal to 0. Now note that the Lambertian operator in this harmonic coordinates that we are using the de Donders gauge, remember? So I can write down this the Lambertian operator in these coordinates as 1 over square root minus g partial mu partial mu on minus g square root minus g mu nu partial nu, and this thing is equal to simplifying a bit is equal to you can take g mu nu partial mu, and you'll add to this 1 over square root minus g partial mu on square root minus g mu nu times partial nu, right? Now remember, we have this, what we started with in fact was that g mu nu is equal to eta mu nu plus kappa h mu nu. So using this and the definition of the harmonic gauge, which was partial mu on square root minus g mu nu, is equal to minus kappa partial mu on h mu nu minus 1 by 2 eta mu nu, and this trace of field h plus higher order terms, of course, and this thing was equal to 0, right? That's how we defined, or that is how the harmonic gauge is defined, right? Now if I look at this thing, that is you can write down your, well, this thing is equal to this thing, right? And this thing in this equation is just this thing. And so what I can do is I can write down this, all of this equation, right? I can set this equal to, or it's the same as g mu nu partial mu partial nu, right? Now from this point I'll use the metric for static external gravitational field, in which our Schrödinger equation is defined, by the way. So the static external gravitational field, what is that? Well, in that we have the 0 0 component of g as 1 minus 2 phi g, and we have the ij components as minus 1 plus 2 phi g times delta ij, and we also know that this phi g is much smaller than 1. Right, now with this I'm going to perform a non-relativistic reduction for the wave function of the field phi, and doing so what I have is that I can write my phi as exponential negative iota m times t times psi of t comma x vector. Now let's just put this back into our Klein-Gordon equation, and upon doing so we find that using of course this g00 gij and this field, we have not square root 1 plus 2 phi g times, we have minus m squared minus 2 iota m partial 0, the zeroth component plus partial 0 squared, and we have minus delta ij, let me just see, yeah, minus delta ij partial I partial j plus m squared on psi t comma x vector, and this is equal to 0. Now let's just make some simplifications. You see that this the mass terms, and these are going to cancel up to the leading order in phi g, and the this partial not squared term is a higher order term in the momentum, right? And so we can drop that out because we're ignoring higher order terms, and so we are left with the usual Schrödinger's equation, that is iota partial 0 on psi is equal to minus del over 2m minus del over 2m plus m phi g on your field psi, right? And this is your Schrödinger equation for a particle that is in an external gravitational field. So with this, let's just stop for now. And in the next lecture, I am going to derive the Feynman rules for gravity by using the second quantization of the gravitational field.